Hi there. I want to bring to you something about hybrid orbitals, and it's the because on why we can do all these things. So I want to relate that to how potential energy as a function of internuclear distance, or in other words, this graph relates to it all. So let's take a look at this graph. Remember when we got like two hydrogens here, which is what this picture is showing? If we want to bring two hydrogens together, as they come closer and closer, we move left on this chart, the two orbitals overlap, and the electrons kind of repel each other, but at the same time we've got this energy of the protons being attracted to the electrons, and that attractive force is the greatest at this bottom part because the Coulombic attraction is so great. That negative number means it's a high Coulombic attraction. So this idea of attracting has to happen when the protons can attract to those electrons. It gets close enough that attractions can be so great. It kind of seems simple when you got two hydrogens, but what if you had this idea of hydrogen, instead of hydrogen, let's say you wanted to make CO2. If you wanted to make CO2, then one of the bonds that you got going on is the C to the O. So let's think this hydrogen is C, and it's attracting to the O. Now what's specifically happening here is you've got carbon, and it has the 1s2, 2s2, 2p2, right? And my oxygen over here is 1s2, 2s2, 2p4. And so what actually has to happen is this 2p has to have to overlap this 2p. And they have to be overlapping so much and so close together that they can have the two nuclei be attracted to each other. Now, if I was to draw a picture of what this looks like in a kind of funny way, you've got your 2s right here. That's your 1s. I'll put my 2s as this orange circle. And then I'll make my 2p here with these bubbles. Remember, like the dumbbell shape, right? And that same sort of thing is going to happen with my oxygen here. I've got my 1s circle, then I've got my 2s circle, and then you've got your green part, which is your 2p's. So you can kind of imagine what I need to do is have this 2p orbital overlap over this 2p orbital without having too much repulsion. But remember, that orange part is underneath there, and he's kind of getting in the way. I mean, look at that. The electrons live in there. That's a lot of repelling. They're going to come closer and closer and closer together. And how are you really going to get this green part of the bubble to overlap this green part of the bubble? Can you see how that would be really tricky? You wouldn't get much of a dip here because it would just have so much interaction, so much repelling that it wouldn't actually have a successful overlap. We have to overlap the bubbles in order to share electrons appropriately. So it's a good thing that the world comes up with a solution to this. Because the way it is, if we keep thinking about atoms as these circles, it doesn't work. You can't have enough of a hybrid overlap. Not hybrid overlap, but you can't have enough of an overlap in general. So let's talk about hybrid orbitals. So here's my picture of that like S and the P kind of bubbles. Can you imagine how we can take this shape and the blue shape and the pink shape and kind of smash them together? Kind of make a hybrid shape between the two and come up with this shape. Now check it out. Let's say you had this shape. Here's your carbon. Has to overlap a circle shape. Can you imagine how these two can overlap each other pretty easily? It might look something like this. Well, that's not so bad, especially when you compare it to this kind of picture. That one you can't possibly overlap very well. But if you got a new shape on the carbon, I can see how this bubble could get a oxygen right over it and have some great overlap. The nuclei, if you're wondering, is right there. Pretty far away, but close enough to feel those attraction to the electrons. So the first big main thing of today is hybrid orbitals. What are they? If you want to think of them as smashing orbitals together to make a new shape, that's exactly what a hybrid orbital is. You're taking the two other orbitals and hybridizing them, or kind of like smashing them together to make a new shape. So now CO2, here's my oxygen. You do not hybridize the outside guys. You only hybridize the inside guys. In other words, the central atoms. So here's my oxygen. It can easily overlap this part of the carbon, just like this oxygen right here can easily overlap this part of the carbon. And you can see how I can make a really good molecule there. In order to make a strong bond, you have to have enough of an overlap of your orbitals, and hybrid orbitals allow that to happen. Let's check out another kind of hybrid orbital. Notice it's called an sp2. S, here's the S, P2, two P's, a P and a P. So here is an S and two P's, and they're smashing them together, and we make, this is like the intermedium kind of shape, you make this shape right here. Well, you check it out, the nucleus is in the center, they've got big bubbles. We have hybrid orbitals in order to make big places for the overlapping to happen. Check out this shape, sp3. So as you might imagine, you've got an S and 3 P's that you're putting together. These are kind of like the intermarry, the different parts of them. I think it's less useful to look at that, but better to look at this bottom part. If you look at the bottom part, you can see that these S and 3 P's kind of mash into a tetrahedral kind of shape. This kind of shape that has 4 parts sticking out. That works really great. We can overlap these big bubbles a lot easier than that other beginning shape that I had tried to draw. A word that I want to talk about here is called degenerate. Degenerate means same energy level. So like when you're thinking about P's, like in a normal carbon, you'd say 1s2, 2s2, 2p, 2. The degenerate orbitals would be anything that have the same energy level, like these 2 P's. The P block has 4 or 3 different shapes, and you'd have 2 electrons in one of the orbitals each. These would be degenerate. Degenerate means same energy level. Now the way carbon is right here, it has 2 P's that are degenerate, and it has a 1s that is degenerate of itself, but not with the 2p because it's in different levels. Now here's your 1s, here's your 2s, and here's your 2p. So anything on the same energy level or same level going up and down is degenerate. Well, what's great about this sp3 is it will create a new energy level sort of thing. And they will all be degenerate or same energy level, same amount of energy. Okay, so let's do our take-home message. Take-home message number 1. Why do we do hybrid orbitals? Because you cannot overlap very well, and we need to overlap in order to get a strong attraction, to have a Coulombic attraction, to have a bond. Idea number 1. Idea number 2, what is a hybrid orbital? It's the smashing to make a new shape. The new shape allows it to overlap better. Big idea number 3, how would I label each of these orbitals? It's dependent on how many things you have on either side. So, in other words, we look at the central guy, here's carbon right here. How many things does he have around him? 1, 2, 3, 4. He has 4 things around him. I know, very technical term. So I would call him sp3. Notice 1s and 3 p's. 1 plus 3 equals 4. 4 things. Take a look at this one over here. Here's an s. It's the number of things, not the number of bonds. He has 1, 2, 3. 3 things around him. sp2. 1s, 2 p's. That equals a total of 3. And there are 3 things around this. Take a look at carbon here. Here's carbon. It's not the number of bonds, it's the number of things. He has 1 here and 1 here. That means he has 2 things around him. So I would call him sp hybridized. He has 1, 2 things, 1, 2, sp. Hope you're getting the pattern. Gets a little tricky down here. 1, 2, 3, 4. He has 4 things around him. This lone pair's electron, they are counted as 1. So there are 4 things. 1, 2, 3, 4. So I'd call them sp. Now I got to add up to 3. So 1 plus 3 equals 4. So it's sp3. sp3 hybridized. Take home message number 3 is, what kind of hybridizing do you have on everything? I count the number of things I have, and then I count, and I decide, is it sp1, sp2, sp3? It's just got to add up to the total number of things. And the last take-home message is about sigma and pi bonds. Sigma bonds are the things that happen between the 2 nuclei. So like if you have a carbon attached to hydrogens here, your first single bond is called a sigma bond. Sigma, 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 sigma. The pi bonds are the things that happen above and below the nucleus. In other words, if you've got carbon attached to a carbon, it's already got a sigma bond there, so if you want to put a double bond in, that double bond has to have electrons that kind of live above and below things. Let me show what I mean by this problem. Let's say I want to count the number of sigma bonds on this top molecule. 1, 2, 3, 4, 5. That first single bond is a sigma bond. There are 5 sigma bonds. And this one right here is the second bond that was made there, and that is called the 1 pi bond that you have. Let me count down here. 1, 2, the first center guy. There are 3 sigma bonds here. This top bond is the first double bond. This bottom bond is the second double bond to make that triple. So there are 2 pi bonds. If I take a look at this one, I'll do one more for you. The number of sigma bonds right here And right here, there are 2 sigma bonds in this one. And these are the 2 pi bonds. Moving a little bit further. 1, 2, 3, 4. There are 4 sigma bonds and no pi bonds in this one. This one has 1, 2, 3 sigma bonds. This guy right here is your only pi bond and 1 pi bond. And then in the bottom one, 1, 2, 3, all sigma bonds, so that there's 3 sigma bonds, and there are 0 pi bonds. Now at this point you can be totally done, but if you're someone who's wondering, like, how do we do this BF3 and ICL3, this is not part of the AP-ness at all. This is not part of AP. You do not have to know this, but a lot of my kids are asking it, so I wanted to shout it out to you really fast. Here's my down and dirty kind of answer. So if you've got BF3, we know in the normal world it's like this, and so I would call this 1, 2, 3. So this would be sp2 hybridized. What that means is when you look at normal boron, he's got 1s, and he's got 1, 2, wait, he's got 1s and 2s and 2p. He goes 2p, 1. So his electrons look like this. And what we do is these outer electrons actually hybridize together. Remember S, P2, they kind of smash together so that now our hybridized B looks like this, 1s. And all these smash together to be called sp2. And these electrons separate out. This little guy just sits lonely, he's just the lonely 2p that's just by himself. And these electrons right here are going to be the electrons that bond. You might be thinking, what about ICL3? ICL3 looks like this. He has 2, 4, like that. And so if I count the number of things around him, there's 1, 2, 3, 4, 5 things around him. So I'd say sp3, that's 1 plus 3. I need to make 5 though, so I've got to get 1 more. There's his D block. He's an sp3d. Now, technically, it's controversial if the D block does it exactly like this, which is why AP doesn't ask anyone to do this part. So you never have to ask about the D part, but that's technically the most leading theory on how they're able to expand their octet. All right, like I said again, these last 2 slides, not on the AP test, but people were asking, so I'm bringing the answers.